Hello again, Physics 243. In this unit, we'll discuss kinetic theory and the molecular interpretation of temperature. So, as I've been saying, temperature was really a mysterious thing, hot and cold. What exactly that was rather mysterious. But people did figure out a way to measure it accurately. And then kinetic theory gives us another point of view. So kinetic theory follows from the atomic theory. Atomic theory is that things that are made out of molecules and atoms. And kinetic theory is the idea that they're all jiggling around like this. So here's a gas, for example, and the molecules, not drawn to scale, are bouncing around inside a box, and they collide with each other and such. So that's the point of view from kinetic theory. And a lot of information can be drawn from that picture. All right, so kinetic theory has a number of assumptions. First of all, large number of molecules. And by large, I mean large, like on the order of Avogadro's number of molecules moving in random directions with a variety of speeds. So it's important so that we can do statistical analysis of things. Another assumption is the molecules are rather far apart on average. So most of the time, the molecules are not interacting with each other and they don't influence each other. Molecules obey the laws of classical mechanics in kinetic theory, and they only interact when they collide. And furthermore, if there are collisions, they're instantaneous and they're perfectly elastic. So the instantaneous part means that we can ignore whatever potential energy might go into, squeezing one molecule into another. And perfectly elastic is important so that we don't lose any kinetic energy at all. Okay. Now, a gas would be contained inside of a container. In kinetic theory, gas pressure is due to collisions between the molecules and the walls of the container. So the walls of a container are continuously bombarded by gazillions and gazillions of collisions, and that's what gives rise to pressure. Okay, so on the basis of these assumptions, one can show that this. So this is an equation which is derived in the book. It's a nice argument. I don't want to go over it now in the interest of time, but I encourage you to read it. It's on page 374. But the result is that we have these macroscopic quantities that describe a gas, the pressure and the volume, right? Volume is the container that is put in. And here it's related to microscopic quantities. So N is the number of molecules that we have. M is the mass of molecules. V is how fast the molecules are going. Right? So that's one nice result that can come out. Yeah, N is the number of molecules. And these square brackets that I have over here, these not square brackets, the angle brackets, they denote an average. So an average over all the molecules. And in particular, we have an average of the square of the speed. Okay, that's what that symbol means. Now, let's recall the ideal gas law, the way we wrote it down before, excuse me. PV equals nRT. And remember that the little n is the number of moles of gas that we have. So that could be expressed as the number of molecules that we have divided by Avogadro's number, Na. Then that can be rearranged like this. Put together the ideal gas constant and Avogadro's number. So those are constants. And in fact, that ratio has a name. It's Boltzmann's constant. It has this value. And it's an important constant that shows up in lots of areas of physics. So the ideal gas law can be expressed either this way or this way. And we're going to use this one in the next slide. Okay, so we have these results. This from that derivation on page 374 in the book, and this way of writing down the ideal gas law. So there are two ways of expressing P times V. So we can set them equal to each other like this. Now we can cancel the N, move the 2/3 over here to the other side, and I also moved the 1/2 m inside the average. It's just a constant, so that's not going to, that's legal, that's allowed. Okay, so look at what we have here. 1/2 mv squared. Well, I'm sure you'll recognize that as the kinetic energy, so we have the average kinetic energy. Average kinetic energy is 3/2 kT. So this is a very important result from kinetic theory. And in words, what it says is the average translational kinetic energy, right? That's this average of 1/2 mv squared of the molecules in an ideal gas is directly proportional to the temperature of a gas, like that. Right? 3/2 K is the constant, so it's proportional to the temperature of the gas. Have you fallen out of your chairs yet? This tells us what temperature is. It finally tells us what temperature is. It's been a mystery up until now. Temperature is a reflection of the average kinetic energy of the molecules. That's what temperature is. If you increase the temperature, you're increasing the average kinetic energy of the molecules. Okay, so now we have a physical understanding of what temperature is. Now we know what hot and cold really is. Isn't that cool? I hope you're enthusiastic about this. I know it's the end of the semester, but this is a really neat result. More than that, the entire distribution of molecular speeds was derived by James Clerk Maxwell and Ludwig Boltzmann in the late 1800s. So this, the shape of this curve has a name, the Maxwell-Boltzmann distribution. And what it tells you is it's a histogram of the speeds of the molecules. So speed is on the horizontal axis, number of molecules vertically. So pick a speed, and the curve tells you how many molecules are going at that speed. All right, so there's one speed that's most probable, right? So what that means is if you count all the molecules the number of molecules that have different speeds, this is the speed that has the most number of molecules going at that speed. Okay, a little hard to say. The distribution also has other features. So the average speed is over here. It's not where the peak is because the right side of this distribution is a little heavier than the left side, if you will. So the average is over there. And there's another characteristic called the root mean square speed, and that's a value over here. So the importance of the root mean square speed is that on the basis of what we have already, we can write down a temperature dependence of the VRMS, the root mean square speed. So let's have a look at that. So the RMS average speed of molecules in a gas. So what is that? Let's start with what we had here. And now I'm going to pull the 1/2 back out. Remember I had put it in before, I just pull it back out. Cancel the 2's and move the m to the other side like this. And then on the left, we have the average of v squared. Let's just take a square root of that. And the square root of 3kt over m. And this object here, that's what VRMS is. So root, because we're taking a square root, mean, because we're taking this average, square, because we have quantity squared of v. So that's what root mean squared means. It's the square root of the average of something squared. Okay, so we have this result, and we see that VRMS, the root mean square speed of the molecules, depends on the square root of the temperature, and inversely with the square root of the mass. Okay, but first let's get a handle on what kind of numbers we're talking about. This is example 1316 from the book. What is VRMS for air? And in particular, oxygen and nitrogen molecules at room temperature. So air at room temperature. Well, we just look up the mass of, say, an oxygen. Let's consider an oxygen molecule. Look up the mass of it and plug it in. So we have 3, there's the Boltzmann constant, the temperature, and here's the mass of a oxygen molecule. We get 480 meters per second, which in miles per hour, if you have more intuitive understanding of that, like 1,074 miles per hour. So these molecules are really zipping along fast. For nitrogen, just look up that mass and plug it in, get 510 meters per second, or 1,141 miles per hour. They're moving really quickly. Okay, so since the RMS speed increases with the square root of temperature, it takes the whole distribution with it. So here's what the distribution of speeds looks like for a cold gas, for a room temperature gas, and for a hot gas. So it shifts to the right. And the reason it gets wider and sort of lower is because we're considering the same amount of gas. So the distributions are normalized so that the area under them is the same, is 1. And that just reflects that we have a tank of a fixed amount of gas, and we look at the distribution for cold, room temperature, and hot. All right, so it shifts to the right like that. But VRMS is also inversely proportional to the mass. So if we take gases at a fixed temperature now, fixed amount of temperature, fixed amount of gas, fixed temperature, and pick different mass molecules, here are noble gases, so these are just the atoms, we see that the distribution for the heaviest molecules, this is xenon 132, is over here in purple, and it shifts to the right for lighter and lighter gases. And again, this is normalized so that the reason why it's getting lower as it spreads out is because we have a fixed amount of gas that we're comparing. All right, so here's the take-home message. Temperature is a reflection of the average kinetic energy of molecules. So this is a great breakthrough in physics. We finally came up with a physical understanding of what temperature really is. For an ideal gas, we got this particular relationship. And here I have Ke instead of K. That just means kinetic energy. Sorry for that. So that equation's for an ideal gas. But in general, this idea that temperature is a reflection of average kinetic energy of molecules applies to everything, liquids and solids, etc. So for our gas, the hotter the temperature is, the faster these little guys move around. But everything is jiggling like that. So here's a big, let's say, organic molecule. And as the temperature increases, this kind of jiggling gets more and more violent. Right? So that molecules are not these fixed things. They jiggle around like this. And that's very important for how they interact with one another. Okay, so that's it for this unit. I hope you enjoyed it.